Okay. Okay, so hopefully now everything works, and then I will I will send the link to the recording. Well, I hope it will be in the same playlist as usually, and will be available soon after the lecture. Okay. Anyway, I will send the notes from this template to everybody. So let's start. Last time we studied the products of algebraic varieties, and somehow the key point was the product of affine algebraic varieties that was related to the tensor product of the corresponding algebras of regular functions, and in particular the product of two affine algebraic varieties was proved to be an affine algebraic variety. So we start today with the projective analog of this claim. So we will prove the theorem due to Italian mathematician Segre, that the product of two projective spaces, Pn times Pl, is a projective variety. Namely, it is a closed subvariety in some big projective space P and L plus n plus L. Okay, and hence if we have two projective varieties X and Y, their product is projective as well. Okay, because you remember that the product of two closed subvarieties is a closed subvariety in the product. Okay, so let's prove this Segre theorem. So in fact, this is called the Segre embedding of the product of projective spaces into some big ambient projective space. So Pn, as you remember, said theoretically is the set of lines in the affine space n plus 1. I mean, passing through the origin, and similarly, Pl is also the set of lines in a L plus 1, and then P n L plus n plus L is a set of lines in a n plus 1 times L plus 1, and this is the same as the tensor product a n plus 1 tensor a L plus 1. Okay, so the embedding is just the tensor product. So a point L in Pn and L prime in Pl goes to the tensor product line. And this will be a line in P and L plus N plus L. Okay, so this is the embedding. We only have to prove that this is projective variety, so that it is cut out by certain equations. Let us write down these equations. So we'll write it down in coordinates, namely in homogeneous coordinates. Say x1, so x0 and so on, xn. So these are coordinates on Pn, and then y0 and so on, yl. Then it goes to the coordinates z, ij, that by definition are just the products of those coordinates, xi times yj, and here I runs from 0 to n, and j runs from 0 to l. Okay. Now, how do we prove that this makes sense? Well, we know that the projective space is an algebraic variety, and at least by one of the constructions, it was covered by the basic open subsets, all isomorphic to affine spaces. And so we can check that this is a morphism in those basic affine spaces. So if we restrict to a basic open subset d xi, or maybe just for short, let's define it. Let's denote it di, and this is in Pn, and given by an equation that the ith coordinate does not vanish, and then because it's defined up to multiplication by a scalar, we can set it equal to 1. Yeah. So x0 and so on, then xi is equal to 1, and so on, then xn. And similarly, we have dyj in PL. Okay, so on these two open subsets, if we restrict our Segre map, then it goes d I, well, maybe I still should keep dxi times dy j, goes to d z ij, namely the set where this coordinate zij is equal to 1. Yeah, just by the formula, because if we multiply 1 at the ith place next coordinates and 1 in the jth place in y coordinates, then we get 1 in the ij place for z coordinate. Okay, and then for other coordinates, it is just a product, so it is really a morphism of a affine space given in these coordinates. Okay, now we proved that this is a morphism, and now I have to prove that this morphism is an isomorphism onto its image, right? So let's check this. So I have to check the Segre morphism. Say sigma is an isomorphism. its image. So the image it is cut out by the homogeneous equations. And somehow, if you think of those coordinates as forming a matrix, and n+1 times l+1 matrix, then the image consists of matrices of rank 1, right? Because they are decomposable. So rank 1.
Почему ранг единицы? Можете еще раз повторить? Почему
Just one moment, let me try to hear you better. So say it again, please.
Почему ранг единицы? Можете еще, пожалуйста, раз повторить?
Just one moment, let me try to close my window so that I can hear you still better. So you ask why the rank is 1, don't you? Well, that's some basic observation in linear algebra. Yeah, if you take one vector, imagine it's a row vector, and another vector, imagine it's a column vector, and then take their scalar product, their tensor product, then the resulting tensor is rank 1. Yeah, I mean, all the columns are proportional to each other, and all the rows are proportional to each other. So the rank is 1, meaning that all the 2 by 2 minors are equal to 0. So the equations are all the 2 by 2 minors are 0. In other words, the determinant z I j, z I prime j, z I j prime, z I prime j prime of this 2 by 2 matrix is 0 for any I prime j prime. Okay. So now let's go to the next page. I'm sorry, you cannot see what was there before, but maybe you'll remember for a moment. So now we have to check that this morphism sigma restricted to the product dxi times dyj is an isomorphism. Onto this subvariety rank 1 intersects with the open subset D Zij. Okay. And how do we do this? We just construct explicitly the inverse. Sigma inverse of z 1 1 and so on. Then Zij is 1, and then so on. Finally, sorry, it starts with 0 0, and then z ml. Okay, this is equal just to the, say, column z z p j okay, times the row z u sorry z I IQ. Okay, so here PP runs from 0 to n, and Q runs from 0 to L. Okay, and there we are. Okay, in particular, the in this column at the jth place you will have 1, and this row at the ith place you will have also 1, right? But by the condition on this open subset D Z I J. Okay, and that's it. So we constructed the inverse isomorphism and proved that sigma is isomorphism on the open subset. Okay. So this is very important. Segre embedding, we will use it many times, and the simplest example is the product of P1 times P1. Then it embeds into P3, right, by our general formula, and it is given by just a single equation. The image sigma cut out by a single equation. I mean, there is just one 2x2 matrix, so the determinant of this single matrix A, B, C, D is 0. So in other words, AB minus BC is 0. Okay, so it's a non-singular projective quadric. So if we have a two-dimensional non-singular projective quadric, then it is isomorphic to the product of two projective lines. And somehow, if I could draw, it can be seen in some mechanical constructions. Yeah, there is one family of lines on a hyperboloid, and there is another family of lines on the same hyperboloid. Okay. Now this is about products of projective varieties. We proved that they are always projective, and hence restricted to open subsets. Oops, sorry. Restricted to open subsets. We deduce that the product of quasi-projective varieties is also quasi-projective. Okay, and now let's go to another topic of separable varieties. I remember that maybe a month ago it was raised by Alexander Gonzalez, but unfortunately now Alexander Gonzalez is not with us. He has a colloquium in functional analysis, but maybe he'll be pleased while watching the recording. So first of all, let's define the graphs of morphisms. Say gamma pi of morphism of algebraic varieties pi from x to y, and this gamma pi certainly lies in the product. So how does it lie there? Well, we have a morphism from X to itself, just the identity morphism, and we have another morphism from X to Y, and this is our pi. And then by the definition and the universal property of the product, it gives rise to some morphism from X to the product, X times Y. Maybe let's call this morphism gamma pi. And then this graph is by definition the image of this morphism. Gamma pi. And well, in general, the image of a morphism can be something bad. It's not necessarily closed or open or any subvariety, but we'll see that usually, at least in favorable situations, the graphs of morphisms are just closed subvarieties. And the condition that guarantees that the graph will be a closed subvariety is called the separable property of Y, of the target. Okay, so first of all, let us somehow express the graph of any morphism from some basic one. So let's go to the next page, and if we take the identity morphism from Y to Y, then its graph is just the diagonal. And that's pretty clear, I hope. And then you have a general morphism pi as before. Then gamma pi is just the preimage of this diagonal. Of delta Y under the morphism from X times Y to Y times Y, that is just pi and identity. Okay, and that's clear just theoretically. And then, if you remember how we defined subvarieties, we just started from any subset and then equipped it with the induced topology and induced sheaf of regular functions. Okay, so from this we have some induced structure of the graph as a space of as a ringed space, and now once again we will see that pretty often it is a closed subvariety, and in particular for algebraic varieties, it inherits the structure of algebraic subvariety. Okay, so the key definition is that Y is a separable algebraic variety if the diagonal delta Y in its square is a closed subvariety. Okay, so somehow in all the meaningful examples we encountered and will encounter, it is so. But certainly there are counterexamples. We already discussed it a month ago. Let me just recall briefly the standard counterexample called Raviola. And this is the affine line with a double point, A1 with the double origin. So it is glued from 2 copies of the usual affine line over the open subset U that is the punctured affine line. Okay, so there are 2 copies, like the upper copy and the lower copy. They are both just A1s, but there are 2 origins, the upper origin and the lower origin in the result of this gluing. Okay, so it's a legal, legitimate algebraic variety, but not separable. Its diagonal is not a closed subvariety inside. Okay, but let's see some basic properties of this good separability property. So first, if we have a morphism with a separable target, then the graph is closed. So Y is separable. And then the graph in the product is closed. Second is that any subvariety, I mean locally closed subvariety, of a separable variety Y is separable as well. And also the product of separable varieties is separable. As well. And finally, all the quasi-projective varieties are separable. So you see that once again, the class of separable varieties is very wide and contains everything we encountered so far and essentially everything we will ever encounter.
Можете напомнить, что означает квази?
Quasi-projective means locally closed in a projective space. Okay.
Спасибо.
Welcome. Fine. So proof. The first part is essentially clear because you see at the top line of this page, gamma f is the preimage under pi and identity of the diagonal in y squared. So if diagonal is closed, then this preimage is also closed. But by definition of topology. Now the second part again is clear because for a subvariety, say x in y, we have the diagonal in x is just x times x intersected with diagonal in y, right? And since delta y is closed, again, its intersection with x times x is also closed. Now, for the product, the diagonal in the product is again intersection of evident things. So you take the projection, say, of to the first and third factors, and the preimage of diagonal delta x, and intersect with the inverse image with the projection onto the second and fourth factors of delta y. Okay, so again, if those diagonals are closed, their preimages are closed, and intersection is again closed. Finally, about quasi-projective, you only have to prove this for projective varieties, right? Because then you take you just apply part B. Yeah, you apply it to subvarieties in projective. So enough to prove for say x equals Pn, and then we use this Segre embedding.
And where did we use the subvariety in part B that the subvariety is locally closed?
What do I mean by locally closed subvarieties?
No, where do we use the locally closed condition? What can we say? Subvariety.
No, somehow we don't. In a sense, we don't use it, but it's just the definition. When we say subvariety, we presume that it's a locally closed subvariety. For us, okay, subvarieties are the open subvarieties of closed subvarieties, okay, or vice versa, closed subvarieties of open subvarieties. Okay, okay, it's just sort of tautology, just a reminder. When I say subvariety, I mean a locally closed subvariety. Okay.
Okay, thank you.
So, but by Segre, we have an embedding of Pn times Pn into Pn squared plus 2n, and then I want to see the diagonal in there, and the diagonal in there is cut out by explicit equations. So delta Pn inside Pn squared plus 2n is cut out. I go to the next page, sorry. By the equations. Remember, we had there z coordinates, yeah, and the z coordinates z ij is equal to z gi for any I and j. So that there we are. Okay. Now the next lemma we'll need. And this applies to arbitrary, not necessarily separable varieties. So if a morphism from one variety to another, and then the graph is always locally closed. In their product. Okay, so we have just proved that if y is separable, then the graph is closed, but for arbitrary y, the graph will be locally closed. So let's prove this, and let's consider the affine open cover of Y. Okay, so then we have the inverse image of those. They cover X. Can open cover. And say pi restricted to this open subset. Let's denote it by pi I. And now the graph of those restrictions are closed, right? Because the affine varieties are separable.
Don't we need to make an extra step here when we say that we consider the pre-image? We want to also intersect because like pre-image might be not affine, it's just open, right? So we need to intersect our open subsets like pre-images with the open cover of X.
No, I don't understand why. I just cover everything with the pre-images of those open affines. I don't care if the pre-images are not affine. I only need that those yi's are affine themselves, right? Since they are affine, they are separable, and hence the graphs of pi i's will be closed. That's the only thing I need, nothing else. Does it answer your question, or did I misunderstand you?
No. Yeah, I forget that we don't care about X being affine. Yeah.
Okay. So those are affine. They're separable. And the graphs of pi I inside well, maybe I should call it xi times yi are closed. Well, and this implies that gamma pi is locally closed, because X is covered by xi. Okay. Okay. And now another useful claim, how to distinguish separable varieties is as follows: the criterion of separability. So X is separable if and only if for any open affine say U, V subsets in X, the intersection is also affine. But that's not enough. We also need that the natural restriction morphism from the product to the intersection is surjective. Okay, so the proof. First, if X is separable, then the intersection of two open subsets U and V is we already used it, this observation that it's U times V intersected with the diagonal in X. Now the diagonal in X is closed, so it is a closed subvariety in the product. U times V. Now both U and V are assumed to be affine. Hence, the product is affine as well, as we argued last time. And the closed subvariety of an affine variety is an affine variety as well. So U times V is affine as the product of affine varieties, and hence U intersection V is also affine. And the restriction morphism K of U times V is the same as K of U tensor K of V, and it surjects onto the regular functions on the intersection because the closed subvariety of a affine variety. Okay, now conversely, somehow the same key observation. If we know this property about intersections of open subsets, then we see that the intersection of U times V with diagonal in X is closed in the product in U times V, but now X is covered by such things, say UI times Vj, and hence delta X is closed. Since it is closed in any open subset. Say it again, please.
I'm sorry, how do you get that
Yes?
the intersection of the product U and V and the diagonal is closed? We know that it's affine. Is it sufficient?
So once again, the intersection of the product with diagonal is the same as intersection U and V, right?
Yes,
as we
and we know that it's an affine variety.
We are given that it is closed in U times V, right? This is our condition. Because we know that at the level of regular functions, this morphism from K of U tensor K of V to K of intersection is surjective. It means that, okay, fine, thanks. So we are done with this. Go to next page. And now maybe let's see a few examples of somehow a priori separable varieties. So algebraic groups. So G, an algebraic variety. And it is also a group. Okay, so we have a multiplication morphism. M from G times G to G with the usual axioms like associativity, the identity element. So this identity is from just point to G, and also the inversion map from G to itself. Okay, so the composition of multiplication and inversion is the map from G to identity. So these are the usual group structures and axioms, but we only require that all the morphisms are algebraic morphisms. Okay, so there are some basic examples, certainly well known to everybody. So first we have the additive group. This is as an algebraic variety, this is just a fine line, and the inversion. Well, the identity is the neutral element is 0. What else? The inversion is just negative x, and multiplication is just the addition, and it's very clear. Now the multiplicative group, GM, as an algebraic variety, this is just the punctured affine line. The neutral element is 1. The inversion of x is x inverse, and the multiplication of x and y is their product. And the higher dimensional analog of this multiplicative group, there are maybe 2 analogs. You can take some power of this group, and this would be a torus, or else you can take GLN. So this is the set of matrices, open subset of matrices, and by n, such that the determinant is not 0. And again, the neutral element is just the identity matrix. The inversion is the usual inversion. And now this is an algebraic morphism just by some standard formula for algebraic complement. And multiplication is the usual multiplication of matrices. Okay, and then maybe next time, hopefully, we will have other examples. So elliptic curves. And they are not affine. As you see, all the previous examples were affine algebraic varieties. And these would be projective. In fact, they will all lie in projective plane. Okay. And why I introduced the algebraic groups here is that they are all separable. Algebraic group G is necessarily separable. And the proof is because the diagonal in G is the preimage of the identity pi inverse of the identity under the following map: pi from G times G to G, and this is essentially the product G H is a multiplication of G and inverse of H. Okay, so loosely speaking, this is G H inverse. So the two elements are equal only if their ratio is the neutral element. Okay, now there's an algebraic morphism, and the neutral element is just a point, so a closed subvariety of our group G, and hence its preimage is also closed. Okay. Okay. There we are. So our next topic will be not related to the separable property, but will be about relation between affine and projective varieties. Will be cones in the affine space and subvarieties in the projective space. Okay. So a cone P in the affine space is subvariety containing the origin 0 and invariant under dilations. So we have the action of the multiplicative group, say GM times C into C, namely lambda and C goes to the product. In fact, you can extend it to the action of monoid, just A1 times C by the same formula. And then when you act by 0, everything goes to the origin, and so you obtain the first condition for free. Okay, so maybe better to formulate this way: for the action of the monoid under multiplication of all the numbers. Okay, now if you recall that the projective space is the space of lines, you see that the cone is somehow made out of lines, and hence it defines some subset in the projective space. It's projectivization. Like this in Pn. So what is this? You take this cone, you remove the origin that it necessarily contains, and then you take quotient with respect to the action of the multiplicative group. Okay, so it lies in an plus 1 with the origin removed, quotient by the action of multiplicative group, and this quotient is just by definition is Pn. Okay. Now we'll need the easy lemma that the dimension. Say, suppose this cone is or even don't even suppose anything. That the dimension of the projectivization is the dimension of C minus 1. Yeah, because you mod out by the action of one-dimensional multiplicative group, the dimension drops by 1. But let's prove it more rigorously. So we cover the projective space by the open, the basic open subsets, like this. And we just cover the cone C just by intersections with the preimages of these subspace. Let's consider the intersection of our projectivization with such an open subset, and then I claim that this thing, if I just multiply it with the multiplicative group, then it is isomorphic to the initial cone intersected with the preimage of this open subset, the inverse di, where we have the projection P from an plus 1 without origin to the projective space. Okay, and how does this isomorphism go? I take some collection, say C0, so on. Then we must have one at the ith position, so on, Cn. And then we have extra coordinate in this multiplicative group. Okay, so this goes to just the product, lambda C0, so on. Then here we have a lambda, so on, lambda Cn. Okay, and there's an isomorphism, and these are open subsets, and the dimension of whatever x times gm is dimension of x plus dimension with a multiplicative group, which is 1, and dimension of x is a dimension of open subset. Okay. So there we are. This proves the claim of the lemma, and maybe let me say conversely, given a subvariety say x in the projective space, the cone over it, say Cx, is the origin with the preimage P inverse of x. So this lies in the punctured affine space. Okay, So you say if X is closed, then this cone is closed as well. And in fact, this is a bijection between closed projective subvarieties and closed cones. So the next lemma. That the ideal J dx of functions on the affine space vanishing on this cone is homogeneous that is generated by homogeneous polynomials. Okay, and this is very clear because the action of the multiplicative group on this cone, the X, gives rise to its action on the space of functions on everything on this cone. So we have the functions on the ambient space, and there is a restriction to the functions on this cone. Okay, and we have the action of the multiplicative group on everything here. Okay, and so you can decompose all these spaces with respect to this action into eigenspaces. So, for example, for the ambient space of functions, polynomials in n+1 variables, the eigenfunctions are just homogeneous polynomials of degree d. Yeah. Okay, but the same works for the function of this cone. So we have some homogeneous generators here, and also homogeneous generators in the ideal. So the kernel here is the ideal, and it's also invariant with respect to the action. Okay, and we can take the generators. There are finitely many generators by the Hilbert-Basis theorem, and then we can decompose them into eigen as linear combinations of eigenvectors, and they will all necessarily lie in the same ideal. So just decompose the generators of this ideal J CX into GM eigenvector. Okay, so there we are. And then we see that if we have a closed subvariety in the project space, then it is the zero set of some homogeneous ideal J in polynomials in n+1 variables. Okay, and then we can formulate the sort of projective version of Hilbert Nullstellensatz about relation between homogeneous ideals and closed subvarieties of projective space.
Почему мы перешли к полю С? Почему мы перешли к полю С, а не, как обычно, произвольное поле К?
Maybe say it again. I don't hear you well enough. Say it again, please.
Здесь поле может быть любым. Алгебраическое.
Oh, sorry. Why it's complex numbers? Yeah, I'm sorry. It's just because of my idiotism. Sorry. Yeah. Sorry. Any algebraically closed field. Yeah. This was your question, Sergey. Yeah. Yes. Sorry about
Да,
that.
спасибо.
Yeah. I apologize. Yeah. Okay. So projective version. Of Nullstellensatz. So say we have an ideal in polynomials in n+1 variables, but it's a homogeneous ideal. And we have a polynomial f also homogeneous. And suppose that f vanishes on this cone. Well, how to say it? Well, just on the zero set. Sorry, just on the zero set of this ideal. But the zero set of this ideal is the cone J is the cone of certain x, and x in Pn is cut out by this homogeneous ideal. Okay, so suppose now f vanishes on this cone, then f to a certain power big enough lies in this ideal. Okay, and maybe a corollary is that if the zero set of an ideal Homogeneous ideal. In the project space is empty, then the homogeneous parts let's go to the next page. The homogeneous part J, say D of this ideal J coincide with the homogeneous part of the whole polynomial ring. For big enough degree. Okay. So let's prove these statements. So for the Nullstellensatz, when we know that the cone of over the zero set of the ideal in the projective space is just the usual zero set of this ideal J in the affine space. Sorry. Okay, and we know that F vanishes on the preimage of this zero set in the affine space. And also F at the origin is also zero because F is homogeneous. So it implies that F vanishes on the whole cone. Okay, and then we apply just the usual Nullstellensatz. We have that F to the power n lies in this ideal for big enough power. Okay, and for corollary, we just apply this Nullstellensatz to the coordinate functions x0 and so on xn. Yeah, so we know that the zero set is empty, so it's contained. I mean, for each of those functions, it vanishes on the zero set, right? Xi to this zero set is zero, so xi to some power and I lies in this ideal, and that's what we wanted to prove. Yeah, let's go back to the previous page for a moment. Yeah, so if the zero set is empty, then the homogeneous part of the ideal coincide with the whole thing. Yeah. So what do we know? we know that the powers of the generators lie in this ideal, and so it means that if D is say bigger than what, probably than the maximum of those ni's, yeah. Then G to the power D coincides with okay. There we are. We just have 4
Сейчас
minutes left.
про максимум, это кажется,
Yes.
I'm not sure it is so obvious for maximum. Maybe we should take the sum.
Maybe the sum, yeah.
I think the
You
sum is
suggest to
better.
take the sum of all those.
Yeah, not the
Okay, I'm
maximum.
ready to take the sum.
Thank
It's fine with me. Thank you. Yeah, so we have just 3 minutes left. I don't know. Maybe let's take a vote. If we have like 5 or 10 minutes left, then I can do something else. Is it okay, or do you have to rush somewhere else? It's
So it's
I
okay.
think the majority is for doing something else. Yeah. Okay. Thank you. So a criterion for non-empty intersections in projective space. So let's first prove something about affine space, and then we'll deduce this criterion. So say lemma. We have two irreducible closed subvarieties in the affine space, x, y, in sorry, the affine space. And suppose the intersection is non-empty. Then we know something about its dimension. Dimension of this intersection is at least the dimension of x plus dimension of y minus n. Yeah. So for example, if you just take two parallel hyperplanes of dimension n minus 1, certainly they don't intersect at all. So this does not work. You have to know in advance that the intersection is non-empty. But if it is non-empty, then we're in a fine shape. And the proof is an immediate corollary of the principal ideal theorem. Namely, we know that the intersection is the diagonal of itself, and so it is the product x times y intersected with the diagonal in the ambient affine space. Now this diagonal in the ambient, in fact, we used this trick before, yeah, when we argued about separable varieties. And now this diagonal in the affine space is given by exactly n equations. So delta A n is cut out by n equations. namely xi equals yi, yeah, for the coordinates. And then x times y has dimension of x plus dimension of y, right? And then applying those equations, imposing those equations one by one, we lose just one dimension at a time. Yeah, but by the principal ideal theorem. Or maybe it's corollary. Okay, so this is proved, and now we can prove the desired theorem about projective intersections. So if x and y in the projective space now, not in the affine, but in projective space, are two closed irreducible subvarieties, then the intersection is non-empty. Well, so if the dimension of x plus dimension of y minus n is bigger than 0, let me say it is greater than or equal to n. Okay. Then the intersection is non-empty. We had to assume this in the affine case, and the projective space, this follows automatically. And the dimension of intersection is at least the same thing. Dimension of x plus dimension y minus n. Okay. And the proof is now immediate, because we know that the cone of x has dimension of x plus 1, the same for the cone of y. We had this lemma half an hour ago, and the intersection contains the origin, so it's non-empty. So we can apply this previous lemma, and any component has dimension at least dimension of x plus dimension of y minus n plus 1. Yeah, if you do the arithmetics correctly, and hence any component of x intersect y, and this is just the projectivization of the intersection of cones, has dimension at least the desired. There we are. Okay. So there we are. Thank you very much. Now I will stop the recording and hopefully send you the notes. Let me save the notes first of all. Yeah. Okay. And hopefully the recording will be available at the same playlist shortly, maybe within an hour or at the worst tomorrow morning. Okay, so I'm stopping the recording.